Okay, I think people are gathering online also. All right, so considering the time, I think we should go ahead to get started. I'm going to just very quickly introduce Henry. I think all the committee already received some forms or information of Henry, so I'm not going to go into that. Just a very quick introduction that Henry started here 5 years ago.
Actually, six. Oh, six
Yeah.
as research intern.
I mean, before that, he actually started as a summer intern there. And that leads to, he actually was majoring in material science in his undergraduate as well as minoring in computer science. And then the summer intern lead him to apply for the program here. So he's joining here officially 5 years ago as a PhD. And now it's jointly advised. So this is a true joint advising situation that was between me and also Professor James Rodinelli in material science. And he has been joining the meetings of the two groups. Basically, he has two communities that he is affiliated with. So he's going to present today his PhD work. And Henry, I think we're talking about 45, 50 minutes, right? And try not to interrupt you in the middle unless if it's truly needed. Okay, so you can go
Okay.
ahead.
Yeah. Thank you, Professor Chen, for the introduction. And yeah, it feels special to make my final presentation in this room where I gave my first one. So welcome to my thesis defense titled Data-centric Design of Combinatorial Material Systems. What? Sorry, still some tech issues. Yeah. So as engineers, we always want to build something cool. This could be vehicles using clean energy, could be more powerful computing, or even something more futuristic. And at the core of all these things are materials. Advanced materials are really what lay the foundation for technological advances. But how do we find better materials? So to design a material is to identify some deployable candidates with the desired properties within a vast candidate space. And this is like searching an island for treasure. So our primary tools for doing this search are experiments and computation. They have worked well. However, the conventional tech approaches are mainly a trial and error approach, which is costly in terms of both time and money, and also very inefficient. But the good thing is the experiments and computation over the years are gathering a considerable amount of data. And with data emerges artificial intelligence, or AI. So could AI be our tour guide to search this island? Yeah, the answer is definitely yes. So there have already been many ways that AI is being used for materials. So here I show some typical approaches. For example, AI could be an efficient predictor or could accelerate simulation to assist in so-called virtual screening. That's finding the good candidates within a large space. Or inversely, we could use generative AI to directly get the material with our desired property called inverse design. AI is also deeply integrated into experiments. They can help plan the experiments, control them, and analyze, decode the complex data. So these bring forward something called self-driving labs. But in all these AI for materials applications, data really holds a central role. So let's put it in the center. By doing that, we get a data-centric view of materials design. So on the left, we have the materials processing and composition, as well as their structures at multiple levels. These are our design space, or input, or X. And on the right, we have the materials properties and their performance in real applications. These are our design targets, or the Y space. We want to do both the understanding from the design variable to the targets, as well as the inverse design to find the good materials that meets our demand. So with data at the center, there are three key tasks to be done. The first is to represent the material structure into a suitable format of digital data called data representation. The second one is to use computation and experiments to acquire the right data. And the third one is to use the data and AI to predict and optimize materials properties. So in today's presentation, I'm going to cover both method development and applications to materials that I have worked on during PhD. And each part corresponds to a key component in the diagram. So let's first see data representation. If we view the material design space as a map, so a point on this map is not a single point. It's a material with its complex structure. For example, this silica structure shown here. If we just call it SiO2 and input this to the AI, it's likely that the AI won't learn much because this doesn't say what the structure looks like or what Si and O means respectively. To train good AI models, we need a machine-readable data that are informative, captures the relative information, and ideally, we also want it to be generally applicable to a wide range of materials. And also, what we designed with this data format could be realized. So there have been so many representations made for materials, and these are the most widely used ones. So most intuitively, we could view materials as just some atomic coordinates together with their descriptors. This is essentially a set of points. It's most flexible, but we are missing the key information here. And to bring those information back in, we could derive some fingerprints from the material's compositions. So these are usually some tabular data for material to describe the materials. This is good, but it's often not realizable. If you design a set of fingerprints, there may not be one material that corresponds to what you design. So, and the third type is graph. Graph is a data structure consisting of nodes and edges, and node feature and edge features. So graph is a very versatile data structure. It can be used in many ways, and we could encode rich information into it. So it's arguably the most widely used one in modern machine learning models for materials, but still it faces some challenges. It lacks the flexibility to represent disordered materials, as we will see. Yeah, let's revisit the material design space. So some points there are single phase compounds, which are relatively simple for a graph representation, but some, like high entropy alloys and molecular mixtures, are what we call the combinatorial material systems. They have a structural complexity at multiple scales. They consist of diverse constituents, and there are various ways of arrangements for these constituents, and they are often disordered. The key challenge here is we don't have a repeating unit in this structure for a graph representation to be applicable. So this brings us to my first research question. How do we represent the materials to capture the critical information? Now let's see this combinatorial complexity in an example, molecular mixtures. So if we have a large space of different molecules and we want to select some and mix them together to form an electrolyte for battery. If we have 200 components and just want to select 3, there could be more than millions of compositions, and this could be infinite if we consider the fractions. So the challenges here are twofold. First, this is a really large design space, so we can't test them one by one. That's why we need a machine learning model. And this brings us to the research question of how we represent this thing to make a machine learning model. Let's take a closer look at the complexities here. So locally, in this molecular mixture, each molecule has its own chemistry and geometry. So to solve that, we could still use the graph representation by viewing each atom as a node and each bond as an edge in a molecule. And we use features to encode the chemistry. And there's a powerful type of machine learning model called graph neural network, or GNN, that could work well on graphs. But there's another level. So globally, the key feature of a mixture is that it's permutation invariant. So this means that 1, 2, 3 should be exactly the same thing as 2, 1, 3. And this should be recognized by the model. So this resembles a set, This resembles a set data structure in mathematics. And there is a deep set model, which gives the principles that a model should follow to be permutation invariant on a set. So we could also view our molecular mixture as set, but there's another complexity. So our molecules have its weight fraction in this mixture. And more tricky thing is this weight fraction doesn't directly mean the influence fraction. Some molecules could be more important than its fraction. So here's our solution to all these complexities. We call this the MOSET model. So MOSET follows the deep sets guidelines, and it takes in a molecular mixture as represented by a set of molecular graphs together with their weight fractions. And it first uses a graph neural network to learn a representation vector for each molecule in the mixture. So what happens inside a graph neural network is we are doing message passing iteratively between the nodes in this graph. And then finally, we read out the graph feature vectors into a global graph level vector. So by this way, we have the molecular representations. Then we need to aggregate them into a mixture level representation in a permutation invariant way. So as we need to recognize the importance or influence, we're using the attention mechanism as to learn that, just as how ChatGPT captures the relations between words. So our attention mechanism takes in a list of molecular representations and tune them to reflect the importance, and then takes into account the weight fraction to form a global mixture level representation. And finally, this is mapped to the mixture property by a feed-forward neural network.
I should understand, you want the permutation invariant to what?
So this is the W and the graph is one single molecule. It permutes as a whole. If you switch two molecules sequence, this should not change.
Permutation invariant within the W's as opposed to W's.
Within the set. So this whole thing is a set. A set, and each element in the set is XW. So you permute XW as a whole. Yeah, so now that we have the model, we first do some benchmark tests against existing models. We do that on electrolyte data collected from experimental literature. So there are in total 1,000 unique mixtures, and the target is electron conductivity. So we are assessing both the Pearson R for how well the model's prediction aligns with the true values, as well as the Spearman R for how well the model correctly ranks the data. So we can see MOSET attains a better accuracy than all of its counterparts. So this tells us that MOSET has a superior predictive accuracy.
Was that training R squared or?
No, testing for sure. Yeah. So all the benchmark results I show here should be testing. Otherwise, it will be cheating. Yeah. And there is a more interesting question to check is what if a model doesn't preserve permutation invariant? To do that, we use a slightly modified version of MOSETs. So instead of aggregation, we're just concatenating the learned molecular representations, and the rest are not changed. So we write the molecular mixtures in different sequences and input to this model. We can see here that, so here are the targets and the predictions. We can see here that the same mixture with a changed sequence is predicted very differently. And we could also see that the accuracy is poor from the range of the axis. So this tells us that permutation invariance is necessary in this case. So now that we have a good model, the next thing we want to do is virtual screening. As an initial demonstration, we predicted the room temperature conductivity for over 10,000 new binary mixtures and made the data available, openly available. But still, now we are limited by a lack of data. We have only 1,000, remember. So when we have more high quality data, when we envision our model to be like an openly available predictor, or even we can use its prediction to build a data platform. So our vision is that it should be the AlphaFold for molecular mixtures to help scientists design electrolytes. And another thing we could do with such a powerful model is the synergy with experiments. As an initial demonstration, our collaborators at UT Austin has used low throughput experiments to experimentally validate MOSET's predictions on some mixtures. These mixtures contain previously unseen molecules, so it's more challenging, but we have a fair accuracy. And moving forward, we are collaborating with the Jeffrey Lopez group here at Northwestern to integrate MOSETs into a high throughput experimental platform. So they are building a robotic system that could automatically make and test electrolytes. We hope MOSETs can both guide their experiments and also benefit from the more data they are collecting. And after finishing MOSET's work, we realized that its applicability is not restricted to molecular mixtures, but other combinatorial systems like high entropy alloys, or HEAs. So HEAs have multiple principal elements, and they can enable some properties that are unattainable in conventional alloys. But the modeling and design of HEA has been challenging because of their complex configurations, and more importantly, because they are disordered and there's no repeating unit for a graph to be applicable. So can we really apply a graph neural network to HEA? So to do that, we still first need to find a representation. So the method we use is to view an HEA structure as a collection of some local environments. And each local environment is a center atom together with its nearest neighbors. And each local environment should have its weight fraction in this HEA. And then each local environment can be easily represented by a graph, because now we have a well-defined unit. And still, this whole HEA becomes a set of graphs with weight fractions. So the familiar data structure again. Now we can seamlessly migrate MOSETs to this data structure. So with slight modifications, we call it LSETs, local environment graph sets. So it's the same model. So I'm going to skip the details and jump to the benchmark results. So this time we are using, we are comparing the models on predicting HEA's mechanical properties, such as Young's modulus and bulk modulus. So we have 7,000 computed data points in total. You can see still, always the benchmark test result is our model performs the best. So not a lot of details, but we see that LSET attains higher predictive accuracy than its counterparts. And remember that we're using attention mechanism in the aggregation model. With the attention mechanism, we could retrieve an importance score for each component. So this provides us with interpretability. We can check which local environment or which element is really important in the HEA. So we first find which elements are frequently identified as the important ones, just based on some different statistics. You can see chromium, cobalt, and so on. These are exactly the elements that are we often see in HEA literature. Oh, sorry. And we could also see the interaction, like how the presence of element 2 affects the importance of element 1. By this, we can see some elements that are not important on its own, but could be a useful additive, like manganese. So this interpretability could help us to extract some insights to guide HEA design. So a summary of this part. In these chapters, we have presented a generic representation and machine learning model for complex disordered material systems. So this could be applicable to materials with the combinatorial complexity, as well as the disordered materials that are frequently encountered in energy and electronic technologies. This answers our representation research question in a general way.
Briefly elaborate on how the disordered is captured. Disordered materials.
Yeah,
right?
so
there's some stochasticity in it, right? I guess.
yeah, so currently what we can handle is completely random. So if we can break down the material into local environments and the arrangements of local environments are completely random, we can use a set to represent them. But if there are short range orders, there needs to be a better way to handle. Yeah, but for HEA, the current best knowledge is there's no short range order. And yeah, if we view the contributions in a broader sense, so on one hand, we have graph neural networks, which are a family of top performing machine learning models for materials. On the right-hand side, we have the disordered materials like HEAs, which could contain some promising materials. So previously, there's a gap for the GNNs to be applicable in HEAs. And now by proposing this representation to address the structural complexity, we're kind of building a bridge to mitigate the gap. Yeah, but still, these more sets and less sets are deep learning models, and deep learning models are data hungry. So this brings us to the second topic, data acquisition. Yeah. Now we go back to this material design space. So this map is actually a combination of materials composition, structure, as well as other complexities. So this is an enormous design space. The question here is, how do we sample this space? Or in more technical language is, what experiments or computation should be conducted to acquire the most valuable data? Yeah, now you may ask, define valuable. Yeah, so there are many criteria to guide data acquisition. These are the three most commonly used ones. So we want data to be representative in the input space. We want to reduce the uncertainty in the target space, and we want high performance if the target is to be optimized. We often call the previous two exploration and the third one exploitation, and they have been the backbone for many sampling strategy. But this is not the end of the story. There are for sure other considerations. For example, the uniqueness in data and the quality of data, which is the focus now. So to check the data quality, we first see how where the materials researchers usually get their data. So these are the three sources where data come from. However, among them, the published literature and materials databases all have some bias because of the like human preference or the unbalanced distribution of known knowledge. So there's a bias, but we can use experiments and computation to acquire new data and hopefully mitigate this bias. Yeah, to see this bias in an example, we grab some data from two commonly used materials databases, Jarvis and the Open Quantum Materials Database. So here we show the distribution of formation energy, delta E, in different crystal systems. From some simple rules of physics, we know that the higher the symmetry of material, the more stable the material should be. But what we observe in these databases are the opposite. So here the lowest symmetry part turns out to be more stable. So this is definitely not right, and we call this the structure stability bias. So to clarify, this bias we are dealing with is a bias in material structure space. So if we know what the distribution of materials data should be like in nature, then this is the deviate from the known nature. But we often don't know what nature really looks like. But we can still define this bias as a lack of representativeness in some parts, like here or here. So although bias is ubiquitous in materials data, its presence is problematic. If we feed a biased materials data to a model, the model will learn something wrong. So our goal here is to first detect the bias and then guide acquiring new data to reduce the bias. So let's first see how we first need a quantitative metric to identify the bias. So we know from information theory that information entropy could tell us the diversity of a set of values. If we calculate the entropy of delta E for a crystal system, we know the diversity of that system. That reflects how well that system is covered. If this value is low, then the system is underrepresented. Now, if we compare the fairness in diversity among different crystal systems, we can identify the bias. So with a quantitative metric of bias, mitigating it can be viewed as an optimization problem. And we propose this framework called an ETAL to systematically address that. So we can iteratively select the underrepresented system and acquire data in that system. Once we select a system, there are some labeled data for which we know the delta E already, and there are some unlabeled that's not calculated yet. We can use the labeled data to train an uncertainty-aware machine learning model like Gaussian process. It can make a prediction for the unlabeled data with both the prediction and the uncertainty. And using the Monte Carlo method, we could transform that into the mean and variance of entropy that would result from adding each data point. So with that, we could use a sampling strategy that balances exploration and exploitation to find the one material that could lead to the most improvement, that's likely to lead to most improvement in H, and calculate it, add to the label data, and repeat this iteratively. Yeah. So we use some experiments on existing data sets to test ETAL. The first question we want to see is, could ETAL really mitigate bias? Because we don't have really unbiased data that follows the nature distribution. What we do is to introduce some artificial bias in the data we have and use both ETAL and random sampling to augment it. So we can see that as ETAL iterates, the H is becoming more fair among the systems. So we see that ETAL is mitigating the introduced bias. And
could you say a little more about the entropy criteria? This is entropy of what?
Uh,
Within crystal system.
Yeah, so
entropy of the response.
the information entropy of the formation energies. So formation energy is a special thing. It controls the stability. So it's not purely a material property.
And that's entropy within crystal systems.
Yeah. Yeah. So we have seven. It's related to that, but not the whole criteria.
Like the entropy is closely related to variation, right?
Yeah. So we want
higher variance.
yeah.
The spots,
the
formation energy.
yeah,
Higher
the formation
variance
energy.
of that, each
Yeah,
system.
that's true. We want, because that measures the stability. We want the data to cover both the stable and unstable regions of the material space.
Wouldn't that some bias too, if you're deliberately choosing a wide range of formation energies within each system, wouldn't that bias your sample?
Well, so yeah, this is more like a philosophical question, but at least optimizing toward this criteria is improving upon the current situation. And if it becomes like, if every system becomes very uniform, it's better than, it's closer to nature than what we have now. Yeah, but we don't know.
Uniform meaning spread.
Yeah, spread out. Yeah, so the data covers both the very stable ones and the very unstable ones. But we don't know what's the ideal situation. We never know.
It's not for optimization, but more for diversity.
It's for, yeah, it's for improving diversity for each crystal system. Yeah, yeah. And we also use the t-SNE method to obtain a 2D visualization of the material structure space. We can see that ETAL is sampling in the last covered regions by the labeled set, but random sampling doesn't have such a focus. So yeah, ETAL is sampling in the underrepresented region as we want. Yeah. The next question to explore is, how does mitigating bias affect machine learning? To do that, we use the datasets collected by both methods to train machine learning models for two mechanical properties, bulk modelers and shear modelers, and compare their performance on a common test set. So we can see that the dataset collected by ETAL shows a systematic advantage. And this tells us that reducing this structure stability bias is benefiting machine learning models for other properties of interest. Yeah, to a quick summary of this part. So we have developed a bias metric and a framework to guide data acquisition for mitigating bias. And that mitigating bias benefits the downstream data-driven models from the onset, from the dataset itself. So this could be used to improve the dataset quality, the small datasets, and also guide the construction of large centralized databases, and also applicable to other domains, not just material science. So this answers the data acquisition question in a very general way. Yeah, so that's all for my method development part. And with that, we really want to apply the methods to advance material science. So that comes the third part. And we show this and we demonstrate this in a specific type of emerging microelectronic materials. So specifically, we're interested in materials that could have a metal insulator transition, or MIT. So these materials could undergo a large, rapid resistivity change upon some external stimuli, such as a temperature change. And because of this property, they are useful in many microelectronic technologies, like it can make the selector memory or radio frequency antennas to be more energy efficient. And it's also useful in some novel computing paradigms, like neuromorphic computing. The design of each material system has its own unique challenges. And specifically for this system, the challenges are mainly twofold. One is with regard to the design space. So this is an enormous design space, as MIT materials could appear in a diverse range of composition and structures. So there could be so many candidates, and the materials and the candidate space is almost disjoint. And the second challenge is with the data. So it's data-centric design. Data is our field. But here, the complex physics of MIT brings a high cost to the computational models. So the data is very scarce. It takes a lot of efforts to collect one data point. But the known data is very limited and scattered in the literature. It could also be far from our design target. So to solve this, actually, we have a long effort, started even before I come. So to give you some context, I have to present some works not done by me, but by previous students. So to collect data, they are using the text mining approaches to find materials and their properties from a large amount of published literature. And with this data, they can build an initial database of MITs and the related compounds. And using this initial data, they built machine learning models to classify whether a material exhibits an MIT, and also get some insights from these models into what features could be relevant. So putting this all together, they could identify some candidate families within that large design space that are more likely to host MIT materials. By doing that, we are effectively narrowing down the search space. And now we could do design optimization within each candidate family. So this is a standard Bayesian optimization approach to optimize some properties for this material family, because this is also not my work, so I'm not going to details. Yeah, but what I do here is I integrate all these works into a materials design framework that's not restricted to MITs, but could also be used to solve other material design problems. As we define our design variables and targets, we could get a knowledge base of literature and use text mining to find the data within those texts. And with the data we find, we could perform virtual screening using machine learning methods and identify the candidate materials families in this process. And this is reducing the options from millions to thousands. And now with a candidate space of thousands materials, we could do adaptive discovery, combining Bayesian optimization and physics-based modeling to identify the real optimal material in this space. And ideally, we could find some promising new materials to be experimentally verified. We could also redefine our criteria and scope and repeat this process. Yeah, you come right on time. I'm going into the physics part. Yeah, so these are the previous work, our previous efforts on MIT design. So, but here, so we have already identified lots of MIT compounds, but still we're facing a trade-off between two target properties we're pursuing: the resistivity change rate and also its speed, as well as the transition temperature. So what we are currently doing is to assemble two different compounds into a superlattice that looks like, it's just like building some Lego of materials to overcome this trade-off. So we want to get a rapid resistivity change with a high change rate, and also transition temperature above but close to room temperature, so that it's useful in a device. Currently, we are focusing on this specific type of superlattice. So within them, the titanium oxide Ti2O3 is a previously identified MIT compound with a 450 K transition temperature, so higher than room temperature. And its transition mechanism is an interplay between the structural and electronic correlation effects. So when temperature goes up, the structure is elongated, and the distance between two titanium atoms along the C-axis is increased. So this so-called dimer is broken. The electrons are no longer confined between two titanium atoms, but opens a conducting pathway. So this drives the transition from insulator to metal. And now we are pairing it with manganese titanate to form a superlattice. So we use computational methods to study this superlattice. Specifically, it's density functional theory, a type of atomic simulations from the first principles of quantum mechanics. And specifically, we are using this type of DFT called DFT plus U with a parameter U that characterizes the electron correlation. A general workflow for DFT is we input the composition and structure of a material and relax its structure to find a more energetically favorable structure, and then use this relaxed structure to compute the electronic properties. So here are some of our key preliminary findings. So these are the electronic density of states, basically shows whether it's conducting or insulating. You can see that without U, the material is the superlattice is a metal, but with U, we have a band gap. It's an insulator. So does that mean that U is controlling the MIT? To check that, remember that C-axis titanium distance plays a role. So we check that parameter. We can see that for pure Ti2O3, our DFT plus U calculation is reflecting this structural change that drives MIT. But for the superlattice, the distance is not changing much. So this tells us that the superlattice's MIT is primarily driven by the electronic correlation effects, not the structural effect.
2.65 versus 2.53, that's considered a big.
Yeah, this is quite big. It's like several percent, 5% or so, but this one is almost nothing. Yeah, so a quick summary of this part. So we have found some preliminary computational evidences of an MIT driven by electronic effects. So this could be potentially faster as it doesn't require a large structural distortion as Ti2O3 does. So this could potentially make the device more energy efficient. But remember, our primary goal is this trade-off. But these two properties are not directly obtainable from DFT, but our experimental collaborators at Duke are making the samples and experimentally assessing these two things, these two parameters. And to put this in a big picture of data-centric design, now we are at the initial data collection stage for the design of superlattices. Yeah. And from the design of MITs, I also identify some outstanding challenges that could be solved. So we call this the property performance mismatch. So when we design a material, a key part is to predict its property. We often predict the property by assuming an ordered structure of the material. However, the real materials live in devices. And when we make the device, the manufacturing and operating conditions could induce a structural transformation from ordered to disordered of that material. Disordered materials have different properties. So a material that's designed to have a good property doesn't necessarily lead to a good performance in a device. This creates a gap between materials design and practical deployment. So to solve that is for sure a big effort. And what we need is something called materials device co-design to concurrently considering the design at two different levels. This would require another PhD, but I just show some preliminary thoughts. So first thing we need to do is to model the operandal structure of materials and its relation to the property under practical conditions. And for this, our representation and machine learning for disordered materials could help. And the second thing is we need a bidirectional information flow between the materials level and the device level design. So this would need some more comprehensive frameworks like the one I showed before. So now, it's a conclusion of the whole presentation. So my PhD research lies at the intersection of AI and machine learning methods and material science. On the method side, we know that AI and machine learning has excelled on simpler data like image and text. And they are growing for simple materials, but they still struggle for the combinatorial material systems. The two key hinders are the complex material structures and the data availability as well as quality. So my works on data representation and acquisition are mitigating these gaps and on the way to broaden AI's applicability to different material systems. On the science side, my PhD research has covered several types of materials vital for sustainability. So primarily microelectronic materials. And I have also touched energy materials and catalysts. So we are gaining deep understanding of the physical mechanisms for these materials and on our way to better materials. So now an outlook for the future. So we can see that material have always been viewed as the bottleneck of many appealing new technologies. They also blame us for being slow to give them better materials. But why is that? So when we talk about new materials, we often say materials discovery. We discover a material by serendipity. And when we do engineering design, we select the materials. So in CAD, you can select a material, but you can barely create one. So how about we integrate materials design into the whole engineering design process? So we can build AI methods and leverage all other methods for materials design according to the need. So here I list some publications that my thesis and defense are based on. And also I have contributed to several papers because of thanks to the amazing collaborations with so many groups. Finally, we come to this part, the acknowledgement. Well, usually it just takes one page, but today is not a Euro day. So first and foremost, I would like to thank my advisor, Dr. Chen, and co-advisor, Dr. Rondinelli. You have been the best advisors and co-advisors. You have guided me into this amazing world of materials design and supported my exploration. So and I also want to thank my other committee members, Dr. Sargent and Dr. Apley. So I can't imagine a better committee for interdisciplinary research because I have one with 4 members from 5 different departments. What could be more interdisciplinary? And none of my work would be possible with my so many collaborators and the funding source that supported my PhD research. And I have been fortunate to work in 2 groups. The 2 groups have been very different. One feels like an AI group, and one feels like more physics, which fulfills my dream of becoming a physicist. But both are really supportive, really good environment. And it's always hard to believe that our first picture together is 6 years ago. This was from my summer visit here. And this was the favorite photos of 2 groups. The past 5 years is not just an education program, but it's a chapter of my life. And this chapter has been a fun one, thanks to all my friends with whom, so together we have explored a lot of areas of this country, and we have always want to put what we learn into practice. Yeah, molecular dynamics and decision under uncertainty. Yeah. So 5 years has been the longest period of my life since I have grown up, but I do have something longer in my life. So to my parents who are online now, it's my pleasure to have been your son for 27 years. And yeah, in this time of uncertainty, you are the certainty you gave me. Your love is the certainty you gave me. And to my girlfriend, Wenqi, who is also online, thank you so I have loved you for 14 years. Yeah, see this date. Thank you for sharing this special moment of my life with me, and I can't wait to share my lifetime with you. Yeah, with that, I would like to thank you all for coming here, and thank you for your support.